All right, so in regard to what's coming down the pike this week, we're going to be talking about chemical equilibrium. Very fun chapter, sets the framework for the majority of the rest of the third 9 weeks. So critically important that you understand chemical equilibrium, and it's going to be more than the basics that you may have learned in honors with just writing KEQ expressions, solving Le Chatelier's principle. We're going to take it to a whole new level here, and this will set you up for success in the acid-base chapter as well as solubility equilibria. I know a lot of you are going to be out this week. We'll do a lot of filming so that you don't miss much, but keep in mind, being here and watching the film, not quite the same thing. Yeah. But we'll do the best we can. For those of you who have seen Le Chatelier's principle before, that will really help you. But we're going to get into illustrative equilibrium calculations. That's the college level stuff. And then I'm going to reserve the whole block day for a lab on Le Chatelier's principle. It's an inquiry-based lab. It's really very good.
What does this lab do?
This lab, I think, is slated for Wednesday for your class. Yeah.
It's slated Friday.
Slated due Wednesday. We can argue about that at the end. Alrighty. So that's what's coming down the pike, and you're looking at a quiz a week from Friday, and unfortunately the quizzes span the weekend. Oh well. This way you don't have to study. It's all good. So, in terms of where we're going, I'm not going to go over all of this right now because it'll be very overwhelming. But throughout the year we've been talking about big ideas. This is the 6th one. This really is the last one for us, although electrochem will fit back into an older one that we partially covered. So it says any bond or intermolecular attraction can be formed. If it can be formed, it also can be broken. And you've seen IMFs already. These two processes are in dynamic competition, sensitive to initial conditions and external perturbations. That's a hard word to say. Perturbations. Gosh, that's a mouthful. And that's what we're going to be looking at here with Le Chatelier's principle. And there's a whole lot in this big idea, and it is very, very complicated. So we're going to move through it a little bit slower than some of the other material that we've talked about. Chemical equilibrium. For the first time this year, we're going to see reactions that run both in the forward and reverse direction. You saw a little bit of it in kinetics when it said fast equilibrium reaction, but a lot of you really didn't know what that was, and now it's all hopefully going to come together. So the questions we're going to consider first, how are equilibrium constants determined experimentally? So we'll take a look at that. We've got 2 labs on that. One's qualitative, one's quantitative. How can equilibrium constants be calculated from other quantities? That'll be very simplistic. How do changes in pressure, volume, temperature, and the amounts of reactants affect equilibrium? That'll deal with Le Chatelier's principle. Very, very straightforward. What effect does a catalyst have on equilibrium? So we'll be looking. It doesn't affect KEQ. And it'll speed up the rate of the forward reaction, but in turn, the backward will go. So it really has no effect, but a question they often like to ask. All right, so the dynamic nature of equilibrium. When you say dynamic, it's opposed to static. So it just doesn't happen once. It's a process that continually goes on. It's almost like bees going in and out of a hive. They don't just go out. They come in, they go out, they come in. So it's a dynamic process that doesn't stop. So at equilibrium, you'll see the forward and reverse reactions proceed at equal rates. That is to say, the rate of the forward reaction is equal to the rate of the reverse reaction. And at that point, the concentrations are going to remain constant unless you do something to disturb those concentrations. So equilibrium is dynamic. We can graph concentration of reactant or product versus time. And what you'll see here is hydrogen iodide gas, which is a reactant, will decrease in concentration over time, and then it will plateau out once equilibrium is established. it will why would the concentration of hydrogen iodide decrease? Because it's a reactant, so it gets consumed. Whereas product concentration's initially going to increase until it too plateaus. At these plateaus is where you've got this time at which equilibrium is established. And now reactant concentrations are going to stabilize and be constant. Products also. It's not to say they're equal to one another, so don't get confused there. Now this is just a freehand sketch on the computer, which is always difficult to do. We'll take a look at molecular representations. Shown here is the reaction that shows the formation of ammonia from nitrogen gas and hydrogen gas. Why would this not be a formation reaction in terms of enthalpy of formation? Because you're forming 2 moles of product as opposed to 1. Okay, so what you're looking at here, even looking at the graph here, if you didn't have the balanced equation, how would you know that hydrogen gas and nitrogen gas are reactants? Their concentrations decrease over time, good, whereas ammonia is going to increase. This also shows quantitatively the relationship between the stoichiometric coefficients and how much substance you have left at the end. So you can see here the 1 to 2 mole ratio between nitrogen gas and ammonia, and the 1 to 3 mole ratio between nitrogen gas and hydrogen gas. Equilibrium is established when those plateau out at that time right there. Okay? Now built in here, I started to do this for some lessons, not for all. Some of the kids liked it, some of it said it was a bit overwhelming, but this is one I definitely wanted to mention in one regard. Toward the end of the course, when we go back and make sure that we have hit every single learning objective, and I think there's like 130 something, you'll see that we've actually hit pretty much every one. There may be 3 that we didn't really hammer, so we make sure that we hit it in the review. And there's a whole tree. When you look at your review book, it'll say big idea, it'll say essential knowledge, it'll say science practice. I mean, it's completely overwhelming. I looked at it the first time and I put it away and I kept teaching. But as I go back now, it almost makes sense. With that said, there is an essential knowledge category, if you will, and one of them falls right here. This is for Big Idea 6, and that's as much as I'm getting into with the nomenclature. It says, in many classes of reactions, it's important to consider both the forward and reverse reaction. And many processes that you observe daily are reversible. One of them makes perfect sense from the get-go. Evaporating and condensing of water. Nothing better than Florida down here. Storm last night. All right? No problem there. You see that all the time. Absorption of a gas, dissolving and precipitating of a salt. You've done quite a bit of this in the lab already. The one I think will be more relevant to you and more understandable is a biological example. It says binding of oxygen to hemoglobin. And so that's essentially what's going on in your body all the time. In the lungs, what's going to happen there is oxygen will bind to hemoglobin, and then it will be delivered to the tissues where it will hop off. So clearly a reversible reaction. That one's really quite complicated, of interest, and I think I'll mention it here, and this gets into kinetics as well. You don't need to know all the nitty-gritty here, so don't panic. Hemoglobin, you know, is a protein found in blood. It actually has 4 oxygen binding sites. It's cooperative. When one hops on, the other guys come to the party, and then you have 4 oxygen molecules bound to hemoglobin, and then they get delivered to tissues, etc. That's why when your body is deprived of oxygen, it's a major problem, because if the brain doesn't get oxygen within 4 minutes, you can be brain dead or at least have certain significant damage to the brain. Always a concern when babies are born prematurely or in a situation where there's no NICU around, but a lot of the hospitals here have those facilities, which has saved a lot of kids. In any event, the same site that binds oxygen also binds carbon monoxide. And whereas this hops off and hops on and hops off, hops on and hops off within seconds, it's very, very quick. The carbon monoxide bonds, and it doesn't hop off for hours. So the kinetics there are grossly different. So when carbon monoxide is occupying all of those oxygen binding sites, then the body's not getting the oxygen that it needs, and that's why people can die of carbon monoxide poisoning. So you guys are all driving now, or just about all of you, and you don't start your car in the garage with garage door closed, right? And you don't close the garage door until you've turned off the car. And I know you think you are the greatest multitaskers in the world, but you know, you've got the radio blasting, you're talking to your girlfriend on the phone, some of you text while you drive, and I don't recommend any of that. Just pay attention when you pull into the garage that your car is off before you close the garage. Some kids perished in Boca because a mother was careless. So be very, very careful there. With all the hurricanes, don't start those generators in your houses or your garages, etc. Be careful. But in any event, what you see here, an equilibrium reaction, on, off, forward and reverse reactions. So that, I think, can be very helpful for you to understand some biological processes. We'll get into some of these, especially here and here. It says dissolution of a solid, so you can dissolve a solid, and then in some cases you can precipitate it out using another ion. Proton transfer and acid-base reactions, this goes on in the body all the time. We'll talk more about that in the acid-base chapter. And transfer of electrons in redox reactions. So you've seen that transfer of electrons, you know how to balance them. And we're going to come back to redox at the end of the year when we talk about electrochemistry. So that'll be good for you. All right, so one way to show a ratio of equilibrium concentrations is through the equilibrium constant expression, abbreviated KEQ. And in the previous chapter, all I wanted you to be able to do was solve KEQ from delta G. You also should know that if delta G is negative, the reaction, of course, is thermodynamically favorable, and the KEQ is greater than 1. And you'll see a little bit more of that here. What I want to do here is review and really delve into it a little bit deeper, because some of you have had very limited work with KEQ. So your general equation is shown there, where the lowercase letters represent the stoichiometric coefficients. Uppercase letters represent the substances, reactants, products. The double arrowhead indicates that the reaction is reversible. When you write KEQ expressions, concentrations of products are in the numerator, concentration of reactants are in the denominator, and the coefficients become the exponents. Note that it is the product of, you don't add these, you will make a mess. And every year in honors, there's always one kid who didn't pay attention and they try and add those. So don't do that. It is the product, okay? The product of the products raised to their stoichiometric coefficient. The product of the reactant concentrations raised to their stoichiometric coefficients. So for example here, if you were asked to write the equilibrium constant expression for the following, one thing you do want to look at is keep in mind only gases and aqueous substances go in KEQ expressions. So instead of KEQ, when we're dealing with concentration, we write KC. You'll see KP for pressure momentarily. There is a whole family of KEQ, and we're going to be getting into this in quite some detail in this chapter as well as the next two. So if you're thinking about KEQ, in this chapter we're going to talk about KC and KP for concentration and pressure respectively. In the next chapter we'll introduce Ka, an acid ionization constant, Kb, a base ionization constant, Kw, water ionization, or they'll say water dissociation constant. And in the chapter after that, we'll deal with KSP for solubility product constant. What you'll also see in this chapter, as well as the Pogel packet next time, is this is when equilibrium has been established, but initially you'll have something called Q. It's written the same way, but here you'll have equilibrium concentrations or pressure. Here you'll have initial amounts, and then in this one you'll see QIP. So there's a whole family of KEQ that we're going to delve into right here for this chapter. All right, so when you write the Kc expression, again, C for concentration, nitrogen dioxide is in the numerator. How come? It's a product. So product pops right there. Its coefficient becomes the exponent. Reactants go in the denominator. Why did I put a 2 right there? Coefficient of 2. And why not a 0 here? Because it's a coefficient of 1, right? All right? You'll use Kc values in equilibrium concentrations, and you can solve for other concentrations. That is to say, if you are given these equilibrium concentrations, you could solve for Kc. If you are given these two concentrations and Kc, you can solve for this one, etc. Very easy process, just watch your math. Sometimes without a calculator the numbers will be easy, but you must know 2 squared is 4 and 2 to the third is 8 and 3 squared is and 3 to the third is, you got it, all right? Got to have good math skills to survive AP Chem. Ready? What's 5 to the third?
135.
What's 2 to the fifth?
32.
Very good. All right. Let's take an example of how to solve for the concentration of a substance. So you've got decomp of hydrogen iodide, temperature specified, and the temperature has to be specified and remain constant, so KEQ values don't change. It produces equilibrium concentrations of hydrogen gas and iodine. They both are 0.0250 molar, and the Kc is 1.84 times 10 to the negative 2. What's the concentration of hydrogen iodide? This is simple algebra. Just watch how you move variables. So what you've got here is your Kc expression, and you'll always start that way. You'll have your products in the numerator and your reactant in the denominator raised to its coefficient. You want to solve for hydrogen iodide, and the easiest way to do that is to interchange that. Let me prove that, and then from here you will just run with it, because you don't want to waste any time in the multiple choice, and that's what I'm unclear with as to why some of you are really struggling with your timing on the quiz. Maybe it was a long one, I didn't think so, but it apparently was. So you've got, what? Is it too little?
Oh no.
Is it too small back there?
No.
I don't know why you guys are sitting so far back. There are seats up here. Everybody took a shower. Everybody smells peachy. All right. Some of you probably know that you can interchange a numerator on one side of the equation with the denominator on the other, right? Do you all know that?
Yeah.
Yes? So I don't have to prove it?
No.
Awesome. So then, whatever rocks your world is fine. Just be careful. So initially this is squared as such, but you don't want to solve for it squared. This is all in your notes. You want to solve for it to the first power. So what would you multiply that 2 by to get this to the first power? A half. So basically you'll just take this to a half, and then this will be to the first. And then it's just a plug and chug situation. And if you can manipulate your variables, you'll be very successful. A few homework problems here will go a long way toward understanding, right?
Yes.
Yes,
Yes?
Yes.
All right. Oh, don't call me ma'am. I'm not that old yet. I'm getting there, though. All right. You're going to plug these in. The KEQ is given. Multiply, divide, take it to the 1/2 power or the square root. The only thing I will say in your calculators is if you go to the 1/2 or the 1/3 or the 1/4 power and you're not doing it as a decimal, make sure you do arrow up and you keep that exponent in parentheses. Otherwise, you're going to make a mess. Here's your concentration. You can always go back and plug this in here and these guys in here and see if your KC comes out, and that's a good check to do. So let's see if you can do this one. So you've got the generation of phosgene from carbon monoxide and chlorine gas. It says if the equilibrium concentrations of chlorine and phosgene are the same at 395 degrees Celsius, what is the concentration of carbon monoxide? Let's do that together, since we're brain dead. All right, let's take a look. You guys don't have your notes today. Sent the remind yesterday. Some of you didn't do the AP Insight quiz. Who did it?
I did it.
I bet you got that. Ooh, I don't want to say that on video, because that'll tell the other class.
I forgot
All right. I only remember one.
I remember both.
All right, we'll talk about it in a minute. KC expression.
Didn't even think about it.
What's the product? What are the reactants? And we have all gases, so they all came to the party. Now, here's the trick. It says if the equilibrium concentrations of chlorine and phosgene are the same, so I'm just going to cancel those, right? Ah. Now I want to know this, right? Okay. So now we can switch them and we just have 1 over KC, correct? And so that's 1 over, what'd they give us? 1.2 times 10 to the 3rd. Now, if they didn't give you a calculator, could you do that?
No. Yeah.
Sure.
Really? So let me show you a trick. Ready? 1.2 would be 6/5, right?
Yeah.
Yes?
Okay.
Go away.
Good afternoon. May I have your attention for a brief announcement? Girls softball tryouts will take place today at 4 o'clock on Field 4. Have a great afternoon here in Cobra Country.
Good luck, Cassidy. So now, what are you going to do? These are going to cancel, right? And you have 5/6. So that's like, 0.8-ish. So 8 times, this would be 8 times 10 to the -1. So that's somewhere around there unless I messed up the math, right?
You can't see. You can't see it.
Well, it's probably a good thing you can't see in case I messed up the math.
No, you
But I didn't. I did it right. All right. We'll leave it there. The bell's going to ring. Bye, film. We didn't.
Can I see my